Alrighty, so we're jumping into section 4.7 here, which covers indeterminate forms and L'Hopital's rule. And we looked at indeterminate forms once already in this course, but now we're going to do this a little more formally. So let's look at this function right here. The limit as x approaches 1 of the natural log of x divided by x minus 1. And what we'll notice is that the limit of the denominator, if we were just to take the limit of the denominator term, the limit of that denominator term is 0. And because of this, what can you not use? So limits are actually very easy as long as you're able to do the quotient rule on them. But most problems that we look at, you're not able to do that. So in this case, you cannot use the quotient rule. And if you go back and you look at the quotient rule for limits, it says the rule only applies as long as the limit of the denominator isn't 0. So we're not going to do this, but formally, if you were to go ahead and do direct substitution to this limit, you would get this meaningless expression here, 0 divided by 0. And we're going to call that an example of an indeterminate form. So I'll classify the other indeterminate forms here in just a second, but this meaningless expression, 0 over 0, is called an indeterminate form. And we get that if you were to inappropriately evaluate the limit through direct substitution. So here it is. I mean, I've said this many times, but let's say it one more time. You may never write the expression 0 over 0 in an equation or in an expression. Instead, you can only use that to label or classify the expression that you're working with. Okay? So let's look at this example here. Suppose the function f of x has a limit of 0 when x approaches a, and likewise as x approaches a for g of x, the limit comes out to be 0. Well, then if you were asked to compute the limit as x approaches a of f of x divided by g of x, if you wrote this statement here, your work would be marked wrong. And I just want to clarify that. You can never write this equals 0 over 0. That would be incorrect. Instead, what you could do is if you were working with this limit, the limit as x is approaching a of f of x over g of x, if you wanted to, you could go ahead and classify it. You point an arrow at it or something like that and say that it has the indeterminate form 0 divided by 0. Doing something like that is okay. That's simply classifying the limit. But notice what I didn't do. I didn't write that it equals 0 over 0. Okay, so let's go ahead and list all the indeterminate forms that we'll deal with in this class. Okay. So let's suppose we've got a limit of a quotient, or some other combination of functions, but if this formally and incorrectly by just simply plugging in the value a into the limit through direct substitution results in this structure right here, 0 over 0, plus or minus infinity over plus minus infinity, infinity minus infinity plus infinity, 0 times plus or minus infinity, or one of these indeterminate powers, then we're going to say that the limit has an indeterminate form. In all of these cases, you are not allowed to write out those expressions. So for example, you could never write that the limit as x approaches a of f of x minus g of x. You could never write that this limit is infinity minus infinity. This would be incorrect, because that's an indeterminate form. Okay, the other thing I want to add here is we're going to focus in on these two indeterminate forms, the indeterminate form 0 divided by 0 and the indeterminate form plus minus infinity over plus minus infinity. So for this indeterminate form here, I will sometimes just say infinity over infinity, and I want you to know that I'm talking about plus minus infinity over plus minus infinity. Okay. Curiously enough, 0 to the infinity power, if the limit has that structure, it's actually not an indeterminate form, and you can prove that that limit is 0. Okay, so here is L'Hopital's rule, and L'Hopital's rule is a specific derivative rule, or a specific rule that allows us to evaluate limits if they have a particular indeterminate form. Okay? There's a lot of nitpicky conditions to using L'Hopital's rule, so be careful with this. First of all, it says, suppose that both functions are differentiable functions of one variable, and that the derivative of the denominator function is not 0, and this is all occurring on some interval I about x equals a, except possibly at a itself. then if the limit as x approaches a, this should say, there's a typo there, f of x over g of x, sorry about that, has the indeterminate form 0 over 0 or infinity over infinity, then the following statement is true. That the limit as x approaches a of f of x over g of x, calculating this limit, is equivalent to calculating this limit. So rather than, one way to look at that is rather than looking at the ratio of the two functions, the limit as x approaches a of the ratio of the two functions, we instead look at the limit of the ratio of the derivatives. Okay? Now it's absolutely essential that you realize that this only applies if the two expressions have, or if the quotient has one of these two indeterminate forms. Okay? So L'Hopital's rule does not apply for all limit problems. And in fact, even if it applies for a limit problem, it doesn't necessarily make it the best option. So let's look at L'Hopital's rule in action here. And I went ahead and just typed this one up for us, and then we'll actually practice a few. Okay? So here I've got this limit function right here. So we could see in terms of the notation I was using before, f of x, the numerator, is x cubed minus x squared. And g of x, the denominator function, is x squared. And so notice that if we were to take the limit as x approaches 0 of g of x, that its limit comes out to be 0, as does the limit as x approaches 0 of f of x. Okay? So if I wanted to classify this problem, I could say that it has the indeterminate form 0 over 0. Okay? Now we've checked that. Now we also need to check, if you go back to the conditions for L'Hopital's rule, we have to confirm that they are differentiable functions. Okay? It's very important that they must be differentiable functions. Okay? Well, notice that f of x is differentiable around 0. In fact, it's differentiable everywhere. And g of x is differentiable around 0. In fact, it's differentiable everywhere. Okay? So we've got differentiable functions, and they have the indeterminate form 0 over 0, which is one of the two indeterminate forms we need in order to apply L'Hopital's rule. Okay, so here I'm taking the limit of the ratio of these two functions, and notice what did I do from this line to this line? L'Hopital's rule says evaluating the limit with this indeterminate form is the same as evaluating the limit of this quotient here, where what have I done? I've taken the limit of the numerator and the limit of the denominator. That is the limit of, or excuse me, the derivative of the numerator and the derivative of the denominator. That is the derivative of x cubed minus x squared is 3x squared minus 2x, and the limit of the denominator function 2x, x squared is 2x. Let me kind of clean that up. Okay. So we went ahead and applied L'Hopital's rule here, and we got this new limit. Well, unfortunately, this is still not a limit that I'm able to evaluate. If I were to classify this, notice that this still has indeterminate form 0 over 0. I don't want to beat a dead horse, but notice that I'm not writing that this equals 0 over 0. I'm simply labeling this problem as having the structure 0 over 0. Okay. So L'Hopital's rule again applies, so I apply it a second time, taking the derivative of the numerator over the derivative of the denominator, and look what function I end up with. In this case, I end up with the function 6x minus 2 all over 2. Looking ahead, if I were to go ahead and do direct substitution on this new limit, notice that I would not have an indeterminate form, so I can go ahead and evaluate it. Okay. So in fact, evaluating this limit through direct substitution, we plug in 0 wherever we see an x, and we end up with -1 as the limit. Okay. So one thing I'll have you notice is that whenever I apply L'Hopital's rule, out of habit, first of all, let me say that I always label what the indeterminate form is. But then as I apply L'Hopital's rule, notice that I put a little LH over the equal sign. And I think that's a good idea, so that way you know and your reader can know how you got from one line to the next. You're saying that it wasn't by an algebraic method, it was by applying some calculus method, in this case L'Hopital's rule. All right, so let's actually look at some other questions now. So here's the problem that we started with, right? This is the limit as x approaches 1 of the natural log of x all over x minus 1. And if you wanted to classify this problem, you would say that it has the indeterminate form 0 over 0. Do you see that? Notice that the limit as x approaches 1 of the natural log of x Why, that limit is 0. And the limit as x approaches 1 of x minus 1, well, that's also 0. So this has the indeterminate form 0 over 0. Okay? All right, I'm going to say it one more time. It would be incorrect for me to write this. It would be incorrect for me to write equals 0 divided by 0. All I'm doing right now is classifying the problem by pointing at it and saying it has the structure 0 over 0. Okay? So now we're going to go ahead and apply L'Hopital's rule, because both the numerator and the denominator are differentiable, and it has this structure 0 over 0. So this gives us the limit as x approaches 1. Notice my limiting value, 1 in this case, did not change. Oops. Okay. So I'm applying L'Hopital's rule, so I'm going to take the derivative of the numerator, 1 over x, all over the derivative of the denominator, which is 1. Okay. Now folks, very important, I didn't just apply the quotient rule here. I didn't apply the quotient rule for differentiation here. I simply took the derivative of the numerator term, 1 over x, and the derivative of the denominator term, which is just 1. Okay. So let's look at this problem now. Okay. We started out with an indeterminate form, but this is not an indeterminate form. So we can use, we can use other limit techniques on this, and in this case, we're geared up to use direct substitution. So let's go ahead and take this limit through direct substitution. So this gives us 1 over 1, all divided by 1, which gives us a limit of 1 in this case. Okay, so I'd now like you to try letters B and letter C on your own. Okay. What I want you to do is make sure you identify what the indeterminate form is, and then if appropriate, apply L'Hopital's rule, okay, and go ahead and evaluate both these limits. Okay, so I'm not filling in the details. I'm going to let you do that, and those details are absolutely essential for applying L'Hopital's rule. But when you do this for question B, you should find that the answer comes out to be 0. And when you do this for question C, you should find out that the limit comes out to be 4. And we'll pick this up in the next video.